Okay. So, last time in calculus class, all right, we were looking at some basic differentiation rules, right, on 3.2 there. The first rule that we started with was, what is the derivative of a constant, right? Derivative of a constant, derivative of a number. Or in other words, conceptually, right, what is the rate of change of the line y equals 7? What's the slope of the line y equals 7? What's the instantaneous slope? Well, it's always going to be 0, right? Whenever your function is equal to a constant, okay, it's going to be a horizontal line, and that means the slope will be 0. So anytime we take the derivative of a constant, it is 0. Okay? We then also did a little discovery here with the power rule. So we did 3 different derivatives here, right? We split the class up, okay? And we got x cubed, right? We saw its derivative using the limit definition became 3x squared. Likewise, x squared became 2x to the 1. And likewise, x to the 1/2 became 1 over 2 root x. Or if we rewrote that, 1/2 x to the negative 1/2. Then from that, you guys used kind of, your own thinking there, okay, to say, oh, well, when we take the derivative of a variable raised to an exponent, right, a real number exponent, it's simply, the derivative is just simply you bring that exponent out front times the x and then the new power is just subtracted by 1, okay, right? So x cubed, the 3 goes out front and it becomes x squared, 3x squared. 2 comes out front, 2x to the 1. 1/2 goes out front and 1/2 x to the negative 1/2 because 1/2 minus 1 is negative 1/2. Okay. Armed with those 2 rules, we then went into some examples here, okay? Upon first looking at letter A, maybe some of us saw that pi squared and you're like, wait a minute, pi squared, that's the power rule, okay? It's the 2 goes out front and it'd be pi to the 1. But then we were like, wait a minute, pi squared is a constant, right? It's just a number. And so when you graph this, it would be a horizontal line. Its slope is going to be 0 anywhere. And so the derivative was just 0. Here, g of t, okay, that cube root of t, we had to rewrite that, and so we had an exponent, so t to the 1/3. Then we can use that power rule, 1/3 goes out front, t to the negative 2/3, and we rewrote that as a positive exponent. But this was a fine answer too. And then 1 over x squared, again, not helpful with the format in which it was written, so we rewrote it x to the negative 2, and then use the power rule again. Okay. We then use a quick application here of that, so finding the equation of the tangent line to the graph of y equals x squared when x is negative 2. So normally what we're doing here when we find the derivative, these are all ways to describe the tangent slope. Okay? But we can also then find the equation of a line that will be tangent to our function at a particular point. All right, just as a quick, if I show you here real quick, okay? When we did this, right, we used the graph of y equals x squared, and we wanted to find the equation of the line that was tangent at the point when x is negative 2. So if I actually graph x squared here, and then I graph this. Now, granted, in order to graph this, I'm going to have to add that 4 over, so it's in a y equals form. So it'll be negative 4x plus 2, and then plus 4, okay? So if I graph these two things, both the function and then the supposed equation of the tangent line there, when I graph it, you'll see, well, there's y equals x squared, and then there you can see our tangent line. And sure enough, it looks as if, right, that it does kind of come through and intersect at a single point and then go right back out like that. If I do the intersect command on my calculator and then find the point of intersection, sure enough, my calculator gives me what we're going to call negative 2, right, and 4. Okay, that is the location where the point of tangency is. All right. So this is a common application of the derivative that we're going to be utilizing. So this tangent line, as it turns out, is a decent approximation of our original function at points that are near the point of tangency. So again, the tangent line can be used to estimate the function. We'll use that idea later near that point of tangency, okay, because it's close in behavior at that point of tangency. Okay. Questions on that one? I know I'm reviewing here. Okay. So anyway, going back then, we could also then throw in some other stuff, right? All the stuff we did up here when we had the power rule, there were no coefficients. It was just, t to the 1/3, x to the negative 2, or 1t to the 1/3, 1x to the negative 2. But we can also throw coefficients in front, and still the derivative is the same we would expect it to be. 2 multiplies out front with a 3 to make 6, lower the power by 1, 6x to the 1. Okay? And so that's the idea of the constant multiple rule. It's nothing special. It's what we would expect to be true. And then finally, we did some more examples there. I won't run through all those, okay? You can kind of see them for what they are. You've got them on your paper, hopefully, too. We have a few more basic rules that we want to get down, okay? And the first we're going to take a look at here are the sum and difference rules, which were necessary for the last two problems in your homework. But again, I'm going to guess that if you had any sort of intuitive sense about what to do, if you weren't completely thrown off, then, you already kind of can guess what this is going to be. The derivative of the sum of two functions, okay, it is differentiable. You can add two functions and take their derivative, and it's equal to just, in this case, f prime of x plus g prime of x. All right, no surprises there. Okay, no surprises there. Likewise here, if we take the derivative of f of t minus g of t with respect to t, okay, again, don't be thrown off by the fact that it's t's instead of x's here. It's just to change the variables up so you're not always used to seeing just x's, that's all. What would this derivative be? What would we write here? Any ideas? It's going to be f prime of t, minus g prime of t. Okay, nothing fancy there. Okay, so when we take the derivative of a sum of two functions, it's equal to taking the derivative of the individual functions and then adding those answers together. Likewise, when we have a difference, f of t minus g of t, okay, it's taking the derivative of that with respect to t. It's just like taking the derivative of f and subtracting then the derivative of g individually. Okay. Now, what operations are not listed here? Multiplication, division. There's a reason for that, okay? And we're going to be seeing that tomorrow, okay? So unfortunately, when you multiply two functions together, it's not like taking the derivative of the individual products and then multiplying those answers together. Likewise with division. When you have two things that are being divided, you can't take the derivative of the individual numerator and denominator and then just divide the answers. It won't work. Okay, that's why only the sum and difference rules are listed here, because only they allow you to take the derivative of the individual pieces and then re-add them back together, or take the derivative of the individual pieces and then subtract them back together. Okay, so 7a here, we'll just jump right into taking the derivative. You can see we have a difference and a sum, so in other words, we can just take the derivative of the individual pieces and then put those operations right back in. So what is the derivative of x cubed? 3x squared. Very good. What is the derivative of 4x? It'll be so negative 4x, the 1 will come out front, multiply with the 4, and this is maybe like one of the trickier ones here. Let me see, I'll do this. Negative 4x to the 1, if that's our function, okay, the derivative of that, the 1 multiplies out with that negative 4, x to the, and then what happens to our exponent? From a 1, it goes to a what? 0. Anything to the 0 power is what? 1. And so this just becomes negative 4. Okay, times 1 if you want to, which is then just negative 4. So the derivative of negative 4x is just negative 4, or minus 4 there. What's the derivative of plus 5? 0, it's a constant, right? Derivative constant is 0. So you can put a little, I'm going to put a little plus 0 in there just so we can see, you guys are just learning this stuff. It's not a bad idea maybe to see where all the different pieces go. All right, but in the future, as we go on, you don't need to write the plus 0 in there, okay? You don't need to write that in there. But it's helpful now while you're still learning it. Okay, this right here, okay, theta. So obviously we'll be taking the derivative here with respect to theta as opposed to x, right? We're just changing our variables around a little bit. That's okay. But I think if I look through here, we have a little bit of work to do, right? I see a root. We don't really take derivatives of roots. We take derivatives of like rational exponents, right? We also don't take the derivative of quotients right now. I need to rewrite this as well so it's not a quotient anymore, right? So it's not division. So before we take its derivative, let's rewrite it some. All right, we'll have negative 1/2 theta to the 4th. Okay, so I'm going to leave that. Plus this 4th root of theta cubed, that becomes theta to the 3/4. Okay, and then this right here, minus 5/2 theta to the negative 3. Bless you. Okay. Minus 5/2 theta to the negative 3. All right. So now we all are in a format where we can take this derivative here. Now we're in a format we can take the derivative. Okay. Everything has got a coefficient and then is like the power rule. Okay. So we'll take the derivative here. Oh boy. Okay. So 4 multiplies out front there to become negative 2. 4 times that negative 1/2 there. Negative 2 times theta to the 3rd. Okay. Plus derivative of theta to the 3/4. Anybody? 3/4 theta to the negative 1/4. Right, again, 3/4 minus 1 is negative 1/4. Minus, but then actually, negative 3, the derivative of 5/2 theta to the negative 3, that negative 3 is going to come out front, multiply with the negative 5/2 and become positive 15/2 theta to the negative 4. Just like that. Okay, you can stop there. You've taken the derivative, right? It doesn't say make sure everything's in positive exponents. We could stop there if we wanted to. Of course, we could rewrite everything using positive exponents. 3/4 times the 4th root of theta plus 15/2 times the 4th root of theta. Okay, alternatively there with all the positive exponents and the roots back in and stuff like that. Okay. Questions on any of that? If you find yourself having difficulty doing because maybe I skipped a bunch of steps there and stuff like that, when you go and take the derivative here, feel free. When you bring that 4 out front, maybe consider writing 4 times negative 1/2 theta to the 3rd, right? If you don't feel comfortable doing all that mental math, 4 times negative 1/2, write it out. 4 times negative 1/2, and then plus, and then the 3/4 theta to the negative 1/4 is pretty straightforward. But then negative 3 times negative 5/2. Oops. So you could do negative 5/2 times negative 3 theta to the negative 4, right? You can kind of write out more steps if you feel like you need to there, right? I went ahead and just multiplied the coefficient with the power when we brought it out front. But if you need to write out more steps, do that here. Show the 4 out front, then multiply with the negative 1/2. Show that 5/2 out front, the negative 3 out front, and then when it became a negative 4 as well for the power. So something to think about there. Okay. Questions on A or B so far? All right, and then we go to letter C. All right, and here is a quotient. All right, can we just take the derivative of the top and divide it by the derivative of the bottom here? No. Okay, we can't do that. That is not one of our rules. We only have that rule for the sum and difference, where if we have a sum or a difference, you can take the derivative of the individual pieces and then add or subtract them. Okay, we really want to be able to take the derivative here as it's written, right? But we can't. So I'm going to do one little thing here to help us. I'm going to rewrite it as t to the 1/2 instead of the square root of t. But now, what do we do here if we want to proceed and take the derivative? It's not in a format where we can take the derivative. Can we rewrite it somehow so that it is in a format we can take the derivative? Any ideas here? Factor out a t in the numerator, exactly right. And so we can cancel it with the denominator. Okay? Alternatively, you could think about breaking it up. I'm going to show that too. So you could break up the numerator over the denominator. Okay, like so. Okay. Or you could do the factoring thing. Let me just proceed with this since that's what I've got right here, right now, and then I'll show you with the factoring too. Okay, so 3t cubed over t, 3t squared. 5t squared over t, 5t. T to the 1/2 divided by t, t to the, what is it? Negative 1/2, right? 1/2, and then this t is t to the 1, so 1/2 take away 1, right? When you divide, you subtract exponents, so 1/2 minus 1, negative 1/2 there. Okay, so that's it. There's our answer, right? We still have to take the derivative. Oops. Oops. So it's going to be 6t plus 5. Negative 1/2 times a negative 1 becomes positive 1/2. And then subtract 1 from your exponent there, negative 3/2. There's our derivative. Okay, there's our derivative. Okay, questions on any of that? Questions on any of that? Like Sean said, you could alternatively factor a t out of the numerator there. The t factored out of the numerator would look something like this. It would be t, 3t squared plus 5t minus t to the negative 1/2 over t, and then you could cancel the t's out and then kind of go from there if you wanted to. Okay, so kind of two different ways to go there. Okay, but what you cannot do is take the derivative of the numerator, divided by the derivative of the denominator. It just won't work that way. And you'll see why tomorrow when we go over the product and quotient rules. Okay? So, what I would like you guys to do real quick is sketch a single period of sine of x for me right up here, and then sketch a single period of cosine of x for me right here. Okay? And I'll give you like a 30-second head start there. So again, one full period, 0 to 2 pi of sine of x, and then right here, one full period, 0 to 2 pi of cosine of x. Okay? Right there. Just one full period from 0 to 2 pi, please. And I will do the same. Don't worry about the second set of graphs there. Okay. And again, sine is the top one, cosine is the bottom one. The name of the functions are kind of below them, which is a weird place for them to be. But sine is in the top one, cosine's in the bottom one there. We're going to be using these graphs to help us determine what the derivative of sine and cosine are. Okay. All right. So let's focus on sine here. Okay, let's focus on sine for right now. You guys can get your cosine graphs done if you need to in the meantime. Remember that one kind of conceptual idea that we have for the derivative, one way to think about the derivative of a function is to think about it as the slope of the function at a particular point. Okay? Can anyone look at the graph here of sine of x and tell me at what point the derivative will be what particular value? So can anyone identify, just by looking at the graph here, the derivative will be this value at this particular point? Can anyone tell me? Just by looking at there? Long, what do you say?
I have it 0.
Yes, the derivative at pi over 2 is going to be 0. What's kind of cluing you in there that at pi over 2, the derivative of sine is going to be 0?
But it looks like flat out.
Yeah, it looks like it's going to flatten out, right? It looks like we maybe are going to have positive slopes here, right? Because like all the tangent lines would have to be positive to kind of touch only once there, right? Not go through it. But then as we go up to here, it's going to flatten out, and then it's going to go down to now negative slopes after it, right? Exactly right. So over here, I'm going to put, so I'm going to leave that 0 here. I'll put like a pi over 2 like right here. And then the graph of the derivative at pi halves, we should have a value of 0. And so I'm going to put a point right at 0 there. Okay? This right there okay, at pi over 2, it looks like f prime equals 0. And so at pi over 2, I'm graphing f prime over here, right? Pi over 2 should be 0. Are there any other points on here that we can look at and say, I'm pretty sure that at this point, the derivative will be this value? Are there any other points here on the graph? Clayton?
Pi over 2?
At 3 pi over 2, what do you want to say the value of the derivative is going to be?
0.
0 as well, right? It kind of bottoms out in this case, and a similar kind of, just kind of like a similar argument to what Long said there. Yep, so, all right, I'll put 3 pi over 2 over here, kind of spread it out some. Okay, and it looks like it's going to be 0 there too. Okay, again. Okay, just like that. Okay. Now, That's kind of taking care of the easy ones. We can definitely tell what the value is going to be. Let's take a look at something, for example, like pi. Let's do the one in between here. Okay? At pi, we maybe can't tell what the exact value of the derivative will be, but what will the sign, S-I-G-N, will the derivative be positive or negative here based on the way that the graph is kind of going? Negative. Why? You got slopes. The slope's got to go down here to kind of like mimic that, okay? In fact, the slope at pi is precisely -1. Okay, in fact, at pi, bless you, it is precisely -1. Okay, so something like that. Okay, I'll say like f prime equals -1. Well, if I went ahead and told you that at pi, f prime was -1, what do you think about 2 pi? It's going to be +1. Exactly right. At 2 pi, it's going to be a +1. And what about at 0? It will also be 1, right? It's going to be positive for sure because we're going up like that, right? And it's going to be the same idea. Yep, at 1. Okay, now let me just connect the dots here. And what is that the graph of? It's cosine. Oh my gosh. It's right there. Okay, that's it. Okay, so the derivative of sine is cosine. Okay, derivative of sine is cosine. So you're probably looking at this one, you're like, well, Mr. Witt, I mean, come on. The derivative of cosine, it's got to be sine, right? Well, let's see. Let's see. All right. So all right, same idea here. Are there any slopes of our function we can tell for sure will be this value? Pi, the slope will be 0. Okay. Anywhere else where we know the slope is going to be 0? 2 pi and it's 0 as well. Yep. So 2 pi and 0. So 0 and 2 pi. Mr. Wood, look at that already. We got zeros, right? 0 pi and 2 pi. 0 pi and 2 pi are zeros. It's going to be sine. Well, let's see. Pi over 2. Okay. What do you think the slope is at pi over 2? -1. Whoa. Sine shouldn't go that way. All right. What about 3 pi over 2? 1. Okay. So let me connect the dots here. What is this a graph of? Negative sine of x. Negative sine of x. Okay. So while the derivative of sine is cosine, easy. Derivative of cosine, negative sine. Negative sine in general. Okay, and so that's our summary here. The derivative with respect to x of sine of x, cosine of x. The derivative with respect to x of cosine of x, negative sine of x. Okay, so there it is. All right. Something that you are now responsible for, and these could show up on the quiz on, excuse me, on Wednesday. Okay, for sure. Turning the page here, we're looking at this. Okay, we're asked to evaluate the following limits. All right, we have never had to evaluate the limit definition of the derivative on sine, and we won't need to. Okay, because again, with the setup like this, what is this limit asking us to do, really? What do we use a limit like this to do? Take the derivative, okay? But in this case, with the way it's set up, take the derivative of what? What is our function according to this setup right here? 2 sine x, exactly right. Let's look at the pieces and pull them apart. We know that in our limit definition of the derivative, we have to have an f of x plus delta x. Well, by golly, there it is. F of x plus delta x, right? It's right in the function there. We have to subtract the f of x. So the quantity that we are subtracting here at the end, that minus 2 sine x, there is the function. Okay? Alternatively, you can look at the first piece of the function and just remove the delta x part, right? Take out the delta x part, and there'll be 2 sine x right there as well. Okay, we take out the delta x. So our function here we can pull out is 2 sine x. And so then its derivative will be what? 2 cosine x. 2 cosine x. Remember, the derivative of sine is cosine. That coefficient there can just stay out front. And so it's 2 cosine x is our answer. This is the kind of question that you will see potentially on like the AP test. Okay, at least 1 or 2 of these like to throw at you. Okay, and like this can kind of set students a little make them a little concerned because they're like, oh my gosh, limits. That was like way back months and months and months ago when we talked about limits. I don't even remember how to evaluate this limit. But really, all this thing is asking you to do is take the derivative. They don't expect you to actually evaluate this limit. They expect you to see, oh, this is the limit definition of the derivative. I want to find the derivative of 2 sine of x here. It's 2 cosine x. There it is. You can use your shortcuts. Okay? Let's look at this one. Okay? What's our function that we're trying to take the derivative of here? So, negative x squared plus cosine x is what I heard? Right. Yeah, we got to be careful here. So why isn't it the negative x squared plus cosine x? Well, remember that it's got to be minus the quantity of f of x. Right now, this is not minus the quantity. It's just minus the x squared and plus the cosine of x. To rewrite this, it will be minus the quantity x squared minus cosine x. A way you can also avoid this too is if you look at the front function here, right? You can see, again, take out the delta x's. What do you have? X squared minus cosine x. So you can also see it there too in that as well if you don't want to, worry about making that mistake. So either way, yes, it is x squared minus cosine x is our function. And so then its derivative will be 2x plus the sine of x. Exactly, because the derivative of cosine is negative sine, minus a negative becomes positive sine of x. And there it is. Okay, there it is. Questions on any of that? Okay, moving on. Next we're going to learn what the other easiest derivative. I guess the easiest derivative that we learned already was the constant function where derivative of constant is 0. The derivative of e to the x is e to the x. Wow. Okay, you're going to have to remember that one, potentially for the quiz too, so don't forget it. Okay, so let's take some derivatives here again. We want to take the derivative of 3 cosine x minus e to the x. Okay, what's the derivative of cosine? Negative sine, so it becomes negative 3 sine x. Derivative of e to the x? E to the x. There it is. Okay, there it is. Go ahead and try letter B. I'll let you guys try that one on your own. Try letter B. Okay, hint, you should rewrite it before you take the derivative. Okay, hint, rewrite it before you take the derivative. Oops. Bless you. Oops. Oh, that's right. Okay, yeah. Maybe one piece of this function looks weird, at least take the derivative of what you can take the derivative of. Yes. In fact, we want to do that. So, an x to the 1 half in the denominator, we put it in the denominator divided off x to the 3, it would be 3 times x to the... And so we read it, so it's not the derivative yet, right? Because we haven't taken the derivative, so... Beautiful, yes. And this one, you don't need to rewrite it. Good, okay. Like here, for example. We had 3 pi over 2k. We brought the k out, but that 3 pi over 2, we didn't have to worry about that. It just stayed 3 pi over 2. See that?
So unless I can like find the derivative of it, I don't use it as a lead, right?
It's e to the 2, which means it's just a number. You treat it like its coefficient. E to the x, that's different. It's a function because it's got the x in it. So we're going to get rid of it.
That's why they use the x equals e to the x, right?
Well, that's what a derivative would be, yes.
Right.
Exactly, yes. So you can just take, you can treat it as like one fraction and then just leave it like the coefficient, so it just stays up front. I see what you're saying. Yes, but this is a coefficient now. It's not a constant by itself. If you were taking just the derivative of 4 pi over e squared, it would be 0 because it's attached to this function. You take the derivative as the whole piece here. Now, I'll show you that yes, within that rule, this does end up being 0, but right now we don't quite have those. So what's the derivative of this? So it's just going to be 4 pi over e squared e to the x. It is itself. It is itself. So it's not the derivative. Okay. There it is. A little shocking. Maybe. Okay. 4 pi over e squared is a constant. 4 pi is a constant. It's a number. Over e squared is a constant. So we're going to treat it in this case like a coefficient, I should really say. 4 pi over e squared is a coefficient. All right? There is nothing that needs to be done with this. Yes, you could combine the e's together if you wanted to. You could rewrite that as e to the negative 2, and then since they have the same base, you could combine your exponents together. That actually is going to put it into a form where we cannot take its derivative, though. Okay? We don't know how to take the derivative of e to the x minus 2, or 2 minus x, or negative 2 plus x. Okay? But with this form, it is just a coefficient. So what's the derivative of something times e to the x, or a coefficient times e to the x? It's just that coefficient again times e to the x there. That's all there is to it. Okay? And again, I wrote this purposely, right? I'm assuming that it would be probably a less of a big deal if we saw something like f of x equals 3e to the x, and then we took its derivative, and we'd probably be more comfortable seeing that its derivative would also be 3e to the x. But the same is true here. 4 pi over e squared, it's a coefficient, just like the 3 is a coefficient here in front of the e. The derivative of e to the x is e to the x. The derivative of a coefficient times e to the x is that coefficient times e to the x. Okay? So that's all there is to it. Any other questions there on letter B? Any questions on letter B? All right, if not, let's move on then. Okay. This is, by the way, this is the last page we have to do. Oh my gosh, we're making great time. Okay, so let's keep going. Determine the points on the curve in which the slope is horizontal or vertical. Determine the points on this curve where the slope of that curve would be horizontal or vertical. Ideas here. If we want to talk about, or if we want to analyze the slope of a function, what should we probably do? Take the derivative, right? The derivative describes the slope of a function at any particular point. Let's take that derivative then. Okay? What is the derivative of 3x? It's going to be 3. 3. Okay, again, that's like x to the 1. So the 1 multiplies with the 3 to make 3. X to the 0 then is just going to be 1, so it's just 3 times 1, or just 3 there. Okay? What's the derivative of 3 sine x? 3 cosine x. Okay, great. We've got the derivative. We have this thing that describes the slope of the curve at any point x. But we don't want to just find the slope for any particular point. We want to find specific slopes. When the slope is horizontal. What's the value of a horizontal slope? What's the numeric value of a horizontal slope? 0. So we want to know, when does our slope is equal 0, right? Is means equals. We want to know when our slope is 0. Or vertical. What's the numeric value for a vertical slope? Undefined. Undefined. Okay. So how can we use our derivative to determine when our slope is or equal to 0? What should we do here with our derivative? Set it equal to 0. Set it equal to 0. 3 plus 3 cosine x. Setting it equal to 0 allows us to say, okay, here's our slope. When does it equal 0? For what x values? Well, we're going to solve this equation now. 3 cosine x equals negative 3. Cosine x equals negative 1. When does cosine of x equal negative 1? At pi. In the interval from 0 to 2 pi, only pi. So, okay, at x equals pi, f prime of x equals 0. Okay, you don't have to write that out, but again, I'm writing it out for your benefit just because this is notes and stuff like that to kind of summarize our findings there. Okay, really the answer, we just need to have a pi there. Okay, now, that's the only place in that interval from 0 to 2 pi where it equals 0. Now we've got to figure out when our slope will be undefined. Okay, and this is a little bit weirder to like kind of imagine here, but when is cosine x ever undefined? It's not undefined there. At 3 pi over 2, cosine would be 0, right? That's not a problem. At 2 pi, cosine is 1. When is cosine ever undefined? Trick question, never, right? It's actually never undefined. It's always smooth and continuous, right? We don't have any asymptotes for the graph of cosine. And so if cosine can never be undefined, then 3 times that will never be undefined, and adding 3 to it will never make it undefined. And so f of x never has an undefined slope. Okay? Never happens. Never happens. Okay? But Mr. Whitmire, how will we know if we have an undefined slope? Well, just hang on there. All right. Let's try letter B. Go ahead. Do it. You guys do it. Okay? Give it a try. Same question. Same question. Determine the points on the curve in which the slope is horizontal or vertical. Okay? Same question. Hint, you should rewrite it before you take the derivative. Denominator power to the cube root of it's whatever you're more feel comfortable with. So the question is, right, when does it ever equal 0? It's just 2x. Yeah, not never with a question mark, never with a period. Or exclamation point, depending on the size. Right, because we have fractions. Fractions can only ever equal 0. It's when it's like 2. It's always 2. There's no opportunity for this to never equal 0. Let's check to see if it also equals.
Okay, well then, but you're still not.
Let's solve this, okay? It's not the same thing as this because when you rewrite this, it's really 2 over x. You see that? There you are on the right. I rewrote that as that. Now, why is this helpful? A fraction can only have equal 0 when the numerator is 0. Right? Another way to solve this is you like cross multiply and stuff, but LP 0, B2 equals 0, B 0 equals solve. So it's like that. It's never equals 0. However, when it's undefined, what x value is, this will be undefined when x is 0. Okay? So at x equals 0, you're going to vertical tangent. Very happy. Let's use that.
Why we can call it a percent too, and let them get cut off which is too. Okay. Good.
All right, let's keep moving here because I want to get you guys maybe a chance to get started on homework. All right. There it is. Okay. So first of all, just give yourselves a pat on the back if you got the derivative right. Okay. That's important, right? That's step one. We got to make sure we get the derivative correct. Okay. Got to make sure you get that derivative correct. All right. 2x to the negative 2/3, or rewritten 2 over x to the 2/3. Okay. We set that equal to 0 to see when the slopes are 0. When will this thing equal 0, though? Never, right? A fraction only ever equals 0 when its numerator is 0. But 2 will never be 0. And so this thing never equals 0. Okay? Geometry of x is not ever equal 0. Never has a horizontal slope. 2 over x to the 2/3 is undefined when x is 2/3 equals 0. X to the 2/3 equals 0, right? When the denominator is 0. So that's when x is 0. So g of x has a vertical tangent when x is 0. Okay. What if we wanted to find, so we have the x-coordinate. We have the x-coordinate, x value is 0. We have the x-coordinate for the location of the point on g of x where we have a vertical tangent. Okay, so again, we have the x-coordinate, 0, for the location of the point on g of x where it has a vertical tangent. How can we find its matching y-coordinate? What could we do? Plug 0 in where?
For the function.
Into the original function. Exactly right. This is the x-coordinate of the location on the original function. How do we ever find a matching y-coordinate? You plug that back into the original function there. So it would be at 0, -5 specifically, right? Because you plug the 0 in. So it would be at 0, -5. Okay, if you want to be that specific. It didn't say to come up with the x and y coordinates. The x location alone is normally good enough. But just, just because we can, we could find the y function. Okay? Questions on any of this? Okay, so you can see why we emphasize so many of those little topics in the prerequisite kind of material that we covered from that summer curriculum packet, right? Being able to remember, how does this stuff equal 0, or when is it undefined? That's kind of like the algebra topics that, we need to make sure that we're fresh on so we can jump into stuff like this and do then the proper analysis with the calculus. Okay, so anyway, moving on here. Final example, 11. Find the average rate of change. Average rate of change. Does that mean derivative? What does it mean? The slope formula, right? You guys did this back in like algebra 2. This is pre-calculus. And not, in pre-calculus you did average rate of change, although you might have. But it was before calculus, okay? BC. So it's the slope formula. y2 minus y1 over x2 minus x1. Over the interval from 1 to 3, so there are x-coordinates of the function h of x equals x squared plus e to the x, and then find the instantaneous rate of change. Instantaneous rate of change means the value of the derivative at each of the endpoints. Okay, so that is the derivative. Okay, so average rate of change, easy peasy. Okay. Okay, we've got the x-coordinates. It's 1 and 3, so I'll just go ahead and do 3 minus 1. How can we use these x-coordinates then to find the y-coordinates on top there? We aren't given those, but how can we find them? Plug them into what? The function h of x. So I'm going to write it out kind of explicitly here. H of 3 minus h of 1, like so. Okay. So that's going to equal h of 3 is going to be 9 plus e to the 3 minus the quantity, right, because it's minus the whole function there, minus the quantity, let's see here, it'd be 1 plus e to the 1 over 2. Okay, maybe I should just put parentheses on that too, so that way it's there. Okay, and so 9 minus 1 gives us 8, e to the third and e to the 1. Can I combine those? No. They both have an e, but they're different powers, so we're just going to have to rewrite it as e cubed minus e to the 1, and then put that all over 2, and then we can leave that as our final answer if we want to. Okay, right there. It doesn't really simplify much more than that. I mean, you could divide everything by 2. You can make it 4 plus 1/2 e to the third minus 1/2 e to the 1 if you wanted to. But it's fine to leave it that way. Okay? You guys go ahead, find the instantaneous rate of change at the endpoints. Okay, go ahead. Take like a minute. Find the instantaneous rate of change at each of the endpoints. Each of the endpoints. We'll talk about giving the graphical interpretation of the results in just a second here. We'll talk about giving the graphical interpretation of the results in just a second, but right now, just find that instantaneous rate of change. Okay? So instantaneous rate of change is nearly the derivative at those values. That's all you have to do. Okay? The slope aspect that you're trying to do there, that slope aspect, that shows up in that limit definition of the derivative. That is what that is. So like by doing the derivative, you're doing that slope formula, but by using the shortcuts, you're just kind of skipping that step. So it's really just taking the derivative. That's it. Okay. Okay, it looks good. Now evaluate it at the endpoints of the derivatives, right? So 1 and 3. So I plug in 2 different values. Mm-hmm. Yeah. This is not a point. This is an integral, right? From 1 to 3, right? So it says integral, and it's used those square brackets there too. So you like this unit heading? Maybe. So 2e to the. Wait. So where did you take your derivative? So it's this function that we're going to take the derivative of. These are separate calculations here. This is so with endpoints. I mean, so find the derivative. Find instant rate of change at each of the endpoints. You're going to find the derivative and then evaluate the derivative at 1 and at 2. So you're going to plug 1 into the derivative, plug 3 into the derivative. Does that make sense? No. What's the derivative? So here's our function. What was the derivative of that function? 2. So 2x, sorry, 2x, yeah, 2x to the 1. What's the derivative of e to the x? No, just the x. Remember, derivative of e to the x is e to the x. That's the last rule we use there. And then evaluate the derivative at those two entities. Each one still in turn. Okay, other questions here? Other questions? Yeah, perfect. Yeah, evaluate at 1. Don't forget to plug 1 into that x too. Right? 30 more seconds here. Then we'll go over this. Okay. There are our slopes, the instantaneous rates of change at each of the endpoints. Okay? Actually, let me just do it this way. All right. So the average rate of change, separate calculation, instantaneous rate of change, it is merely finding the value of the derivative at instantaneous, the value of the derivative at the particular points. In this case, it was just the endpoint. So I find the derivative, 2x plus e to the x, 2x to the 1 plus e to the x. Plug in 1, plug in 3. Okay, don't forget to plug in that 1 and for both x values there. Okay, both x's. Okay. Remember that when we were first talking about derivatives, right, we talked about finding the slope of the secant line. And we found the slope of the secant line using the slope formula. So this right here is the slope of the secant line. Okay, that's another way of thinking of it. Slope of the secant line is that. Whereas these two, right, these are both slope of tangent lines. Of h of x at, and the first one, x equals 1, and this is the slope of the tangent line of h of x at x equals 3. Okay. So instead of being asked for the average rate of change, you could be asked to find the slope of the secant line. It's merely the slope formula. y2 minus y1 over x2 minus x1. Instantaneous rate of change, or slope of the tangent line, right? That would be, or your instantaneous rate of change, another way to think about it, right? Those are the values of your derivative at particular points. Okay? Notice, for the average rate of change, you need 2 points, 2 numbers, in order to find that answer, right? You can't find the slope without 2 numbers. For the derivative, you only need 1 number because it's a tangent point. It only needs 1 point. The line intersects at 1 point with your graph there. Okay. So that's the idea. Questions on any of that? Yes?
Why is the second tangent line, why is it 6 plus e to the, oh, is that e to the third?
It should be e to the third. Yep, sorry, that is an e to the 3 there. No, thank you for clarifying. I want to make sure it was clear there. Yes, it should be e to the 3. All right, your homework is on Google Classroom. I suggest you get your books out and get started on it, okay? It's more practice with this, okay? So now, up to this point, including tonight's homework, that will be what the quiz will be based on Wednesday. And of course, speaking of homework, I got to come around and collect your homework from last week. So please make sure you have those out, and I'll come out and get them. Yes. Oh, about the homework, okay. Right. That one I kind of jumped because I skipped some steps in some of these. Okay? There's 2 main types of, well, let me finish my video here first and then I'll help you out here more.